Hi, I am Laurent. Welcome to part 2 of the DVA tutorial. We are now going to enter the world of dynamical variational autoencoders. And this part of the tutorial will be structured as follows. We are first going to specify the configurations of data sequence modeling that we address. In the present tutorial, we are going to explore how to link observed and latent vector sequences. And to do that, we will first consider a very classical framework, which is the state space model. As we will see later, that some of the DVA models clearly inspire from the state space model framework. Actually, they can be seen as a generalization of the state space model framework to deep learning and to the VAE methodology. This is, for example, the case of the deep Kalman filter or deep Markov model that we will consider next in details. Then we will examine two other DVA models, the stochastic recurrent network and the variational recurrent neural network. And then we will present more rapidly a series of other models. And finally, after this journey among the DVA models of the literature, we will discuss the DVA as a class of models. We will take some time to present how this general class encompasses or unifies all the presented models and what are its main characteristics. So let us begin with some general considerations on the modeling of sequential data. In the DVA framework, we have two data sequences. We have a sequence of observed vectors, x1 to capital T, and we have an associated sequence of latent vectors, z1 to capital T. And note that x can be continuous valued or discrete valued, whereas we consider only the case of continuous valued latent vectors. Generative modeling consists in defining the joint distribution of both the observed sequence and the latent sequence. And in the so-called driven mode, we additionally have a sequence of external input vectors, u1 to capital T, which values can be continuous or discrete. For example, in control theory, u1 to t and x1 to t are respectively the input and the output of a dynamical system. Generative modeling then consists in defining the joint distribution between the three sequences, or equivalently, the joint distribution of the observed and latent sequences conditioned on the input sequence. Some DVA models were originally defined in the literature in the driven mode, and those models can be reduced to the undriven mode by simply removing the input sequence. And some other models were originally defined in the undriven mode, and those models can be extended to the driven modes by, of course, adding an input sequence. And in all the following, to simplify the presentation, we will consider all models in the undriven mode. That is, we will only consider a pair of observed and latent sequences. Moreover, in this tutorial, we will only consider the case of sequence-to-sequence encoding and sequence-to-sequence decoding. This means that a sequence of T observed vectors is encoded into a sequence of T latent vectors with a one-to-one correspondence, and then the sequence of T latent vectors is decoded into the sequence of T observed vectors with the same one-to-one correspondence. In the literature, this sequence-to-sequence encoding and decoding is also referred to as many-to-many encoding and decoding. So this comes in contrast to the other models that were proposed in the literature and that achieve many-to-one encoding and one-to-many decoding. This means that in this case, the whole observed vector sequence is encoded into a single latent vector z or decoded from this single vector z. This is common practice in natural language processing with discrete observed variables that usually represent words or with continuous latent vectors. And we have an impressive set of recent papers dedicated to text modeling and generation based on this principle. And this principle of many-to-one encoding and one-to-many decoding is also related to VAEs designed to model images, where a quite large sequence of pixels is encoded into and decoded from a single latent vector z. In both cases, NLP and image modeling, we will not detail the corresponding literature. We will really focus on sequence-to-sequence encoding and sequence-to-sequence decoding. So let us now start exploring the models of the literature. And we start with the state space model. The state space model is a very famous family of models that was introduced by Rudolf Kalman in the 60s, where the latent vector zt takes the role of an internal state of the model that varies over time, and for each time index t, zt conditions the distribution of the observed vector x. In terms of joint distribution, we thus have the product over time frames of a transition distribution, P of zt given zt minus 1, also known as the dynamical model and parameterized by a set of parameters denoted theta z. And this density is multiplied by an emission distribution, P of xt given zt, also known as the observation model, and parameterized by a set of parameters denoted theta x. This process is represented by the graphical model here. We can see on this graph that zt depends on zt minus 1, while xt only depends on zt. Depending on what we choose for the transition and emission distributions, we can have many different models and solutions. This is why we speak of the state space model family. And we can mention two well-known examples: the linear Gaussian state space model with the continuous valued state vector, and the hidden Markov model with the discrete valued state vector. So we have already said that we would only consider continuous valued latent vectors in this presentation, so we won't talk much about HMMs in the following. However, let us talk a little bit more about the linear Gaussian state space model. In this model, the transition distribution is a Gaussian with a mean vector that is a linear function of zt minus 1. As for the emission distribution, we also set a Gaussian with a mean vector that is a linear function of zt. And this is done here for convenience, but this is not mandatory. The observation model is to be adapted to the nature of the data. And we see that the two covariance matrices do not depend on the state, but they usually depend on time. Let us now consider the inference problem. So in this data sequence framework, inference consists in estimating the state vector sequence from the observed noisy vector sequence. So it is equivalent of the encoder task for the VAE. We say that the inference is causal if at each time step t, the past and present observations are used for estimating zt, and it is non-causal if the whole observation sequence is used. For the linear Gaussian state space model, with the Gaussian observation model, there exists an exact causal inference solution that is analytically tractable and that is widely known as the Kalman filter. And there exists also a non-causal solution that is the Kalman smoother. And in the causal case, we have this equation for the so-called filtering recursion. We can see that the posterior distribution of z given the past and present observation vectors at time t can be expressed in function of the same distribution at time t minus 1 and in function of the generative distributions. And therefore, the parameters of this posterior distribution can be calculated recursively from the parameters at previous time step and from the current observation vector and from the parameters of the generative model. The mean vector of this posterior distribution is used as the state estimate. In the non-causal case, the Kalman smoother requires bidirectional recursions, that is, filtering from the past and filtering from the future of the observation sequence. And for those who are familiar with HMMs, but not so familiar with state space models, this is very similar to the well-known forward-backward algorithms for HMMs. Talking about forward and backward, it is easy to find examples of the extraordinary impact of the Kalman filters in modern technologies. This is a real excerpt of the dialogue between Mission Control Center and spacecraft. Okay, great, but now what if we need to solve a problem that is more complex than sending people on the moon? Just like, say, modeling speech signals, for example? Well, now that we have settled the ground with the very classical state space model framework, we can now go calmly towards the deep Kalman filter and the deep Markov model that were proposed by Krishnan and colleagues in those two papers. And in fact, we have two papers and two different names, but the generative model is the same or almost the same in the two papers. It is the inference model that is different. So in the following, I will use indifferently DKA for DMM to refer to this model. The nice thing when presenting the DKF DMM is that a large part of the work has already been done a few minutes ago, because the joint distribution in this model follows exactly the same factorization as in state space models. We have the same product between an instantaneous observation model and a first-order state model. Thus, the graphical representation that shows the structure of variable dependencies is also the same. We still have Gaussian distributions, but the important point is that now the parameters of those distributions are non-linear functions of zt-1 and zt, respectively. And these functions are implemented with deep neural networks. So in other words, we have two deep neural networks, one for the transition distribution. It takes zt-1 as input and it outputs both the mean vector and the vector of diagonal entries of the covariance matrix. This matrix is assumed diagonal. And we have another DNN for the emission distribution. It takes zt as input and it outputs both the mean vector and the vector of diagonal entries of the covariance matrix. This matrix is also assumed diagonal. And if we look again to the emission probability, we can see that for each time index t, it looks very much the same as the conditional distribution of a VAE. And therefore, DKF-DMM can be seen as a VAE with a first-order Markov model on the latent variable. And finally, it is very important to note that, as for the VAE, the posterior distribution of the latent sequence given the observed sequence is not tractable due to the nonlinearities. So here we do not have any analytical solution, such as the Kalman filter. And as for the VAE, this implies that we have to define an approximate posterior distribution, that is an inference model. And before we do that, it is interesting to think about the structure of the exact posterior distribution. What are the dependencies between variables in the exact posterior distribution? To answer this question, we can first use the chain rule, and then the exact posterior distribution factorizes as a product of conditionals. We have a product over time frames of the distribution of zt, conditioned on all previous latent vectors and on the complete sequence of observation vectors. And then this posterior distribution can be simplified based on the so-called deseparation principle. Deseparation is a method that is precisely used to define the dependencies in a posterior distribution of a Bayesian network, given the dependencies in the corresponding generative model. Briefly stated, some of the conditioning variables in the expression of the posterior distribution of a given variable can vanish depending on whether the nodes in between those conditioning variables and the given variable represent variables that are observed or unobserved, and depending on the direction of the dependencies. I will not describe it in more details here, since it is described in papers or books on Bayesian networks, in Christopher Bishop's book, for example. So, using deseparation, here we get this simplification. That is, the dependency over previous latent vectors is limited to the single previous latent vector, and the dependency over the observations is not causal. It is limited to the present and future observations. In short, we can say that all past information is summarized in zt-1, and x t to capital T is used for inference because zt was involved in the generation of this future subsequence. Okay, so now that we know the structure of the exact posterior distribution, it is reasonable to assume that a good candidate for the inference model, that is Q phi, would have the same structure of variable dependencies as the exact posterior, so that it uses the relevant information, or say the natural information. If we look at the literature, this is where the two papers by Krishnan and colleagues differ. This principle was followed in the second paper, Krishnan and colleagues 2017, at least for one of the several proposed inference models, but it was not followed in their previous paper 2 years ago. So let us focus on the inference model proposed in the second paper. We see that it follows the structure of the exact posterior distribution, and the conditional posterior at time t is a Gaussian, and similarly to the generative model, the mean vector and the diagonal of the covariance matrix are non-linear functions of the conditioning variables, which are here zt-1 and xt to capital T, and these non-linear functions are implemented with deep neural networks. And the dependency on zt can be handled by a simple feed-forward fully connected layer, or say a multi-layer perceptron, while the sequential dependencies on present and future observations require the use of a more sophisticated process like a recurrent layer. So this is where we need to introduce recurrent neural networks. This is quite a classical issue in deep learning, so I will do it briefly. Basically, an RNN introduces an internal recurrent state variable, ht, that is a non-linear function of the network input at time t and of the previous state. And the output is a non-linear function of the state. So it looks quite similar to the state space model, except that the state relations, the state expression is deterministic, whereas it was formulated in a stochastic framework in state space models. In the graphical representation, we use diamonds to represent a deterministic state, whereas we use circles for random states Z. In the basic single-layer RNN introduced by Kalman in 1990, both functions were hyperbolic tangents applied to affine transformations. And in practice, those functions can be implemented by any recurrent unit, such as long short-term memory units or gated recurrent units. And in the following, for concision and simplicity of presentation, we will keep this generic notation for the RNN internal state, whatever the type of RNN that is used. Okay, so now that we have defined RNNs, let us see how they were applied in the inference model of DKF-DMM. We have seen that the inference model is a Gaussian distribution with parameters that depend on previous latent vector and on present and future observations. The dependency on present and future observations is implemented with a backward RNN that we denote GT, with the right to left arrow on the top to denote the backward or anti-causal form of the dependency. So in short, GT is a function of GT plus 1 and the current observation. And then basic feed-forward fully connected fusion layers are used to integrate the dependency on ZT-1 in addition to the one on GT and provide the posterior distribution parameters. All this process is summarized in this graphical model. Please note that, as for the generative part of the model, mu denotes both the mean vector of the posterior distribution and the nonlinear function implemented with feed-forward fully connected neural networks that provides this mean vector. And this is the same for the diagonal of the covariance matrix. And this will be the same in all the following of the presentation for the other models. So in short, here, mu and v act as fusion networks combining ZT-1 and GT. Okay, we have a generative model, we have an inference model. We can now apply the VAE training methodology That is, we can derive an evidence lower bound for the DKF DMM model. We start from this generic expression of the evidence lower bound, which is simply a generalization of the VAE evidence lower bound to data sequences. Then we replace the generative and inference models with the factorizations that we have seen in the previous slides, and we obtain this expression here. We simply recall below the different terms that were defined in the previous slides. We have the emission model here, the inference model here, and the transition model here, and all of them are Gaussian with parameters provided by deep neural networks. How do we calculate and maximize this big expression? First, for usual distributions such as Gaussians, the Kullback-Leibler divergence can be computed analytically. This is good news. However, this is not the case for the two expectations. Moreover, we do not have an analytical form for Q of ZT given the whole observed sequence. We only have one given ZT minus 1 and XT to capital T. To solve this problem, we can exploit the chain rule to reshape each expectation in a cascade of expectations, as shown here. This result is valid for any arbitrary function of ZT. And then we can compute the expectations sequentially. And when doing that, each individual intractable expectation in this cascade of expectations can then be approximated with the Monte Carlo estimate using recursive sampling combined with the reparametrization trick that we mentioned for the VAE training. The resulting objective function is differentiable with respect to all neural network parameters and can be optimized using stochastic gradient descent. Simon will now illustrate more concretely the functioning of the training algorithm.
In this tutorial, we will not present the training algorithm for each dynamical VAE model that we will review. Actually, the principles that are used to train all the DVA models are quite similar. That's why we will present them only once with the example of the DKF model. I have to mention that the training algorithm that I'm going to present now is a bit simplified compared with the one proposed in the original DKF paper, essentially in terms of neural network architecture. But the general idea is the same, and hopefully it will allow you to easily understand the principles behind training DVAs. So we start by taking one data sequence in our training dataset that we map through an anti-causal recurrent neural network. Doing so, we obtain a sequence of RNN internal states, GT, that encode the anti-causal dependencies on the observations required by the inference model, as Laurent explained. We have seen that the VLB has to be computed sequentially over time, in particular using sequential sampling of the latent vectors from the inference model. So first, we have to initialize the VLB and the sampled latent vector at time step 0, for instance with a vector of 0 coefficients. Then we will iterate over the time steps from t equals 1 to capital T in order to accumulate the VLB over the time steps. This process directly refers to the fact that we have a sum over the time steps in the expression of the VLB that Laurent presented. For each time step t, we compute two quantities. First, we map the sampled latent vector z tilde at the previous time step t-1 through a feed-forward fully connected neural network denoted by MLP here. This network outputs the parameters of the transition distribution of the generative model, which characterizes how the latent vector at time step t is generated from the one at time step t-1. This distribution is a multivariate Gaussian, so the network outputs the mean vector and the diagonal of the covariance matrix. Then we have a second feed-forward fully connected neural network, which takes as input both the latent vector z tilde at the previous time step t-1 and gt, the internal state of the RNN which encodes the dependencies on xt to capital T. This network outputs the parameters of the inference model, which is again a Gaussian distribution parameterized by its mean vector and the diagonal of its covariance matrix. At this point of the training algorithm, we have all the required quantities to compute the regularization term of the VLB, which is simply the Kyle divergence between the inference model distribution and the transition model distribution. Now that the parameters of the inference model are computed, we can sample from the corresponding Gaussian distribution using the standard reparameterization trick in order to obtain z tilde at time step t. Of course, at the next time step, this will become z tilde t-1. We then map this sample through the decoder network, which outputs the parameters of the emission model distribution, which again is Gaussian. This directly gives us the reconstruction term in the VLB. Once we have accumulated the terms of the VLB for all the time steps, we can update the model parameters with typically a step of gradient ascent. Note that in practice we usually average the objective function over a mini batch of training data sequences before updating the model parameters. So to conclude about DKF-DMM, we have seen that in the generative model, DKF-DMM does not explicitly account for long-term dependencies between the latent and the observed variables. In other words, the generative model does not involve a recurrent neural network. It only includes a first-order Markov model for the latent vectors. For DMM, the inference model does take into account long-term dependencies of the latent vectors on future observations by using an RNN. This RNN allows the inference model to comply with the structure of the exact posterior distribution in terms of random variable dependencies. Let us now discuss a model with other types of temporal dependencies. This model is called STORN for Stochastic Recurrent Network, and it was introduced in 2014 by Bayer and Ossendorfer. In STORN, the generative model is defined by the following factorization of the joint distribution between the observed and latent data sequences. It's the product over the time frames of p of zt times p of xt given x1 to t-1 and z1 to t. Before defining these two distributions, let us first compare with DKF-DMM, which follows the structure of standard state space models. We have seen that in state space models, the distribution over zt in the generative model is called the transition distribution, and it corresponds to a first-order Markov model. Here, in STORN, there is no transition modeling over the latent state, as the latent vectors at different time frames are assumed independent. On the contrary, the emission or observation model, characterized by this distribution over xt, is more complex than in state space models. We could say that it's an autoregressive model, as xt is not only generated from the latent vectors z1 to t, but also from the previous observations x1 to t-1. As for standard VAEs, the prior over zt is Gaussian, with zero mean and identity covariance matrix. The observation model over xt is also Gaussian, with the mean and diagonal of the covariance matrix provided by an RNN whose internal state is denoted by ht. This internal state follows a recurrence relation which encodes the causal dependencies of xt on the conditional variables in the observation model, x1 to t minus 1 and z1 to t. This is very similar to what Laurent explained for the KFDMM inference model, except that here for STORN, an RNN is used for the generative model. Theta x here in the emission model denotes the parameters of the RNN and also the parameters of potential feed-forward fully connected layers on top of it, represented by mu theta x and v theta x. In the figures on the right, we have two graphical representations of STORN generative model that we call the compact and the developed forms. The compact form in the top figure corresponds to a standard Bayesian network showing the dependencies between the random variables in the model. But it does not show how these dependencies are implemented using RNNs. That's why we also show a developed form in the bottom figure containing the deterministic internal state of the RNN. For all the other models that we will present in this tutorial, we'll show both compact and developed graphical representations of the generative and inference models. As will be discussed later, we believe that it is important to explicit the two forms when defining a DVA model. Let us now move to the inference model of STORN. It's defined by this factorization here, where Q of zt given x1 to t is Gaussian with a mean and diagonal of the covariance matrix provided by an RNN whose internal state is denoted by gt. Similarly as before, this RNN encodes the causal dependencies of zt on x1 to t at inference time. The RNN parameters, along with potential feed-forward fully connected layers on top of it, are denoted by phi. Importantly, this inference model does not follow the structure of the exact posterior distribution, which is given by this factorization. We see from this factorization that a posteriori, zt depends not only on x1 to t, but also on z1 to t minus 1 and xt plus 1 to capital T. These dependencies were omitted in STORN inference model, which may of course impact the performance of the model. The two figures on the right represent STORN inference model in the compact and developed forms. In the compact form, yellow arrows indicate dependencies that are missing to be compliant with the structure of the exact posterior. The VLB objective function for STORN is given here. As usual, it contains a reconstruction accuracy term defined by the emission model and a regularization term defined by the chiral divergence between the inference model and the prior model. We remind here all the distributions involved in this VLB, where HT and GT denote RNNs that encode the dependencies of XT and ZT on the conditioning variables in the emission and inference models, respectively. In this VLB, the regularization term can be computed analytically. It's the chiral divergence between two Gaussians. The expectation in the reconstruction accuracy term is intractable. So, as usual, it is approximated by a Monte Carlo estimate using samples that are drawn from the inference model. As we have seen in STORN inference model, the posterior dependencies of ZT on the previous latent vectors Z1 to T minus 1 were omitted. So here the sampling does not need to be recursive, which makes it simpler compared with DMM. But again, this simplification may impact the performance. As before, using the reparameterization trick in the sampling process leads to an objective function which is differentiable with respect to the generative and inference model parameters. So it can be optimized with variance of gradient ascent. Let us now mention a few remarks about the generative models in DMM and STORN. DMM considers a first-order transition model on ZT and an instantaneous observation or emission model on XT. So the generative model does not take into account long-term dependencies between the latent and observed variables. Of course, DMM generative model could be extended to take such dependencies into account with a more complex observation model, for instance. STORN considers a simpler transition model on ZT compared with DMM. Actually, no dynamical model is considered for the latent vectors, which are assumed independent and identically distributed. But the observation model on XT is much more complex compared with DMM, as it is autoregressive and it considers infinite order dependencies on the latent vectors. Of course, there's nothing preventing us from using a more complex transition model in STORN. For instance, one could use a first-order Markov model as in DMM. In fact, the most complete model that one could think of is in terms of temporal dependencies is given by applying 2 times the chain rule on the joint distribution of the observed and latent data sequences. This leads to the following factorization of the joint distribution, which again gives a product of an observation model on XT and a transition model on ZT. It is important to understand that no approximation is made to write this factorization. The chain rule of probabilities allows us to write a joint distribution as a product of conditional distributions. To do so, we have to choose an ordering of the variables, and here we chose it so that it leads to a causal generative model. If we want to sample from this model, we would first sample ZT given the past latent vectors z1 to t minus 1 and the past observed vectors x1 to t minus 1. Then we would sample xt given the current and past latent vectors z1 to t and the past observed vectors x1 to t minus 1. This factorization corresponds to the general form of a causal DVA generative model. Laurent will give the general definition of the DVA class of models later with more details. Importantly, each temporal causal extension of the VAE that we found in the literature can be seen as a particular case of this general DVA model. By particular case, we mean that with additional conditional independence assumptions, the above factorization could be simplified. Let's take the example of DKF DMM and STORN. In the transition model of DKF DMM, ZT is assumed to be conditionally independent of x1 to t minus 1 and z1 to t minus 2, given zt minus 1. For the emission model, xt is assumed to be conditionally independent of x1 to t minus 1 and z1 to t minus 1, given zt. For STORN, zt is assumed to be independent of all the conditioning variables in the transition model. So the simplifications are even stronger compared with DMM. However, no conditional independence assumption is made for the emission model. In DVAs, a first-order temporal dependency can be implemented with a basic feed-forward fully connected neural network, and temporal dependencies of infinite order are implemented with RNNs. This implementation of random variable dependencies using neural networks can be done in many different ways, so that different DVA models differ not only in the temporal dependencies of the variables, but also in the implementation of these dependencies using neural networks, in particular RNNs. This is also the reason why we think that providing both the compact and developed forms of the models is important. As I said, Laurent will come back to this general definition of DVA models later. For now, let Xavi discuss a bit more about this relationship between random variable dependencies and their implementation with RNNs, with the example of another representative DVA model called VRNN.